Our project was to design a complete driven double wishbone rear suspension for a racing car.
For Group 9, the key allocated values were 255 kg vehicle, a 75 kg driver mass, a friction coefficient of 1.35, and a center of gravity height of 0.15 meters. These values set the baseline for the later load transfer, braking force, and bearing calculations, so they were treated as fixed design inputs. The wheel package was also fixed as Type 3, using a 6x13 rim, a 20-inch tire diameter, and a 183mm tire.
The wheel rim was built around the Type 3 limits, as mentioned earlier. The rim uses a two-piece rim design, with the central part bolted to the outer rim, making the wheel simpler to manufacture and assemble. The central area was reinforced with lug bolts, since this is where the loads transfer into the hub. Overall, the design meets the packaging requirements while staying lightweight, practical, and realistic with the modelled tyre tread.
From the force calculations, the brake disc was sized around the required braking torque into 209mm diameter, although the ideal size was closer to 192. The larger diameter mainly adds weight, so the disc center was heavily cut out to reduce mass while keeping the contact ring and mounting points structurally sound. The material was selected in EduPack by filtering key properties including hardness, thermal conductivity, strength, density, and cost, leading to a final cast iron selection. To confirm FEA integrity, in Abacus, the caliper clamping load was modeled as a uniform pressure of 0.5 newtons per square millimeter on each swept contact face. The results show a peak von Mises stress of around 0.58 megapascals and negligible deformation, confirming that the final disc design remains structurally safe under the applied braking load.
The hub and shaft were first verified using the updated Excel sheet, including initial component dimensions. The selected material showed to be 4130 steel, chosen for its strength and suitability. The final design equivalent stress was below the material stress, so the shaft passed the fatigue design criterion. As shown on the CAD model, the hub spins with a wheel, which is attached using 3 bolts, and an inner M8 bolt connected to the CV adapter, designed this way for ease of disassembly. The Excel result was then supported with the Abacus braking simulation, with a stress below the yield strength and the allowable stress.
We started the bearing selection by testing a range of possible bearings, including deep groove ball bearings, double row angular contact bearings, and tapered roller bearings. Each bearing was checked against the same criteria: axle load capacity, static load rating, and dynamic life. At the same time, we wanted to keep the upright as compact as possible, because the bearing arrangement directly affects the upright width and hub packaging. To reduce the assembly width, we minimized the gap between the two bearings and selected a 2mm clearance. This gave a center-to-center bearing spacing of 22mm for our bearing choice. This final arrangement passed the static and axle checks. After filtering the options, the SKF 32009X single-row tapered roller bearing gave the best result. We used it as an opposite pair so axial loads could be supported in both directions.
The upright was designed as the main load-bearing component connecting the wheel assembly to the suspension system within the double wishbone setup. A central ball was included to house the bearing assembly and maintain smooth wheel rotation while limiting deformation under high loading conditions. The upright connects to the upper and lower wishbones for swivel ball joints, while an upper bracket was added for the toe link pickup point to reduce overall mass. To minimize local stress concentrations, the pushrod mounting point was integrated into the lower wishbone rather than the upright itself. Material selection was carried out in EduPack, leading to the selection of aluminium 6061T6. The final design was analysed in Abacus using loads obtained from suspension force calculations. The simulation provided a maximum stress of 125 megapascals and a maximum deformation of 0.16 millimeters, giving a safety factor of approximately 2.4 and confirming that the upright remained structurally adequate under the applied loading conditions.
An adapter was created to fix the CV joint to the hub, fixed by 6 equally spaced bolts. 7 dowel pins were used to transfer the torque from the CV joint to the hub, securing its rotation. The selected 7M5 pins arrangement was tested in an Excel calculator under different loading conditions, but the most relevant was the repeated stress, giving a torque capacity of approximately 523 Newton meters, above the demanded torque by a margin of 61.
For the suspension, we used a double wishbone layout as suggested, first choosing approximate pickup points and iterating from this to reduce forces in each member. The final setup uses a nearly horizontal lower wishbone from the side view, a shorter angled upper wishbone, and a horizontal toe link from the side view. A pushrod was mounted onto the lower wishbone and connected through a rocker to the spring, helping package the damper neatly whilst reducing the toe link loading. Finally, the members were checked for tension, buckling, bolt shear and bracket failure. S550 MC steel was used for the wishbone tubes and Cromley steel was used for the brackets. All calculated failure loads were above the calculated loads in the wishbone members, and improvements for the design were derived from this and mentioned in the report.
And here is the final design with all of the components.
Thank you very much for watching.